Hi, my name is Brian Caffo, and this is the Multiple Variables lecture in the regression course on in our data science series. This lecture is co-taught by my co-instructors Jeff Leake and Roger Pang. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. What we're going to talk about in this lecture is the difficult topic of navigating when you have multiple predictors and choosing a model, and what are the consequences of including variables that you shouldn't, or not including variables that you should. Okay, so first point I'd make is we have an entire class on prediction and machine learning. So we're going to focus on modeling. So if all you care about is prediction, you have a different set of criteria. You have potentially different needs for interpretability and standards for generalizability. So it's just a different problem. So in modeling, our interest lies in parsimonious interpretable representations of the data. So we want a small model that's a good representation of the data that teaches us something in an interpretable way. So I like to think that there is no such thing as a correct model. And my friend Scott Zeger, who's a renowned statistician, often says that a model is a lens through which you look at your data, so that you can, the right model is whatever model connects the data to a true parsimonious statement about what you're studying. So a complicated model where you don't learn anything is less interesting than a parsimonious model where you learn something that's true. So there's so many ways that a model can be wrong. You can have the sampling assumptions wrong. You can have the distributional assumptions wrong. You can have the linearity wrong. You can have which covariates are included or excluded is wrong. There's a lot of ways. So we're just going to talk about, in this lecture, variable inclusion and exclusion. And then, I think something that comes up a lot in this class, good modeling decisions are context dependent. So, just as an example, a good model for prediction versus one for studying mechanisms to establish causal effects, those aren't the same thing. If you want predictions, you may be able to tolerate a lot more variables in your model than if you want to create kind of small parsimonious causal effects. So Donald Rumsfeld had this interesting quote, kind of infamous quote, I guess, and it goes like this. Donald Rumsfeld is a former Secretary of Defense of the U.S., and he said, there are known knowns. These are things that we know we know. There are known unknowns. That is to say, there are things that we know we don't know. But there are also unknown unknowns. There are things that we don't know that we don't know. At any rate, it's kind of a funny quote that, or interesting quote that kind of gets talked about a lot in statistics because it relates very well to what we think about. So in our context, maybe known knowns are regressors that we know and have, and we should check whether or not they need to go into the model. Known unknowns are regressors that we'd like to include in the model, but we don't have. We either didn't collect or can't collect them. And then the unknown unknowns would be regressors that we don't even know about that we should have included in the model. Okay, so I like to call that the Rumsfeldian triplet. So some general rules about variable inclusion in regression models. So omitting variables tends to result in bias, unless the variables that you omit are uncorrelated with the variables that you're interested in are uncorrelated with the omitted ones. So this is why, in case you're wondering, we randomize treatments, or why randomized trials, randomized experiments are the standard for evidence, right? Because if you want to look at something, say a treatment effect, and you're worried you didn't include a variable, well, the randomization gives you some hope that the treatment assignment is uncorrelated with these unknown unknowns. Now, of course, if there's way too many unknown unknowns, then just by chance, they're going to be aliased with your treatment effect. which is a problem. And because they're unknown, you don't know how many there are. But randomization to date is probably the best strategy around for trying to balance unknown confounders. But often you can't randomize. So at any rate, so if you can't randomize and you really do need to include a variable in the model and you omit it, then it's going to induce bias in the variables, in the coefficients that you're interested in. So then you might say, okay, well, why don't I err on the side of caution and just throw everything into my regression model? So including variables that we shouldn't have increases standard errors. Any new variables, it turns out that including any new variables increases the standard errors of the regressors. And I want to emphasize this point, it increases the actual standard errors, not the estimated standard errors. So what happens with the estimated standard errors remains in question, because there's two parts to the standard error of a regressor. There's the part that depends on the residual variance, which you have to estimate, which residual variance has to go down if you include a regressor, even if it's unrelated to the response. And then there's the other part that involves the x's in the standard error. At any rate, what you can show is that the actual standard errors, not the estimated standard errors, have to go up if you add new variables. So you don't want to add unnecessary new variables. So another thing is the model always just tends towards perfect fit as the number of non-redundant regressors approaches n. By non-redundant, I mean the model doesn't do anywhere if you include x and 2x and 4x, right? Those are all just the same variable with a different multiplier. But if you include x and y, and if you have a response y and there's 20 measurements, and you include 20 regressors that are just simulated random noise, then you will achieve perfect fit, even though those regressors have nothing to do with y. R squared increases monotonically as more regressors are included, so the proportion of the variation in the y's explained by the regressors increases monotonically regardless of whether the regressors are important. And the sum of the squares errors decreases monotonically as more regressors are included. So here, just as an example, here's a bunch of simulations for the number of variables included for n equal to 100. And in this case, the way I did it, so this is a different set of simulated data for each number of regressors. That's why it's all kind of bouncy like this. So no actual regression relationship exists in any simulation, right? So you can just see I'm just putting random noise into a regressor, into a response, and you see as you get up toward 100, you're guaranteed to get 100% of the variation explained in the y's. So let's look at variance inflation, and like I said, this is a statement about the true standard errors. So I'm going to do a simulation to look at the true standard errors. So my n is 100, and I'm going to do 1,000 simulations, but you can bump that up to 10,000 if you want the Monte Carlo variation to be small. Okay, here's our three regressors, x1, x2, x3, and then what I'm going to do is I'm going to get a bunch of things called betas. And that I'm just going to grab the coefficient for x1 from every linear model fit. And I'm going to do it number of simulations times. And what I'm going to do is I'm going to fit the y given x1 and regression model, and then I'm going to add random noise. So this simulation part of it is adding random noise a bunch of times, 1,000 times. And then I'm just going to so that's how I generate my y, and then I'm just going to fit three regression models, one that includes only x1, one that includes x1 and x2, and one that includes x1, x2, and x3, and in each case I'm going to grab the coefficient for x1, and then I'm going to, so what have I done? I've repeatedly simulated from the regression model, and I've gotten the beta 1 coefficient, And so I'm going to look at that distribution, and the standard deviation of that distribution is the population standard error of beta 1. Okay, and what you can see is in the first case where we only have x1, we get a standard error of 0.028. Then it goes up a little bit higher, 0.02872 if we include x2 in the model, and then it goes up even a little bit higher if we include x3 in the model. That's variance. That's the variance inflation. But you can make the variance inflation much worse if here's our x1, which is a normal, but now instead of x2 being just another random normal, I made x2 a average of some random normals and x1, a kind of average. And I did it so that kind of how related to x1 it was. In this case, it's I think I did it by square root 2 so that the variance of x2 remained 1. In this case now, the variance of x3 is also 1, but x3 is highly related to x1, right? It's sort of 95% x1 and a lot less a percent x2. So then I just did the same thing, and now you can see for x1, here's my standard error estimated by simulation. If I include x2, right? If I include x2, which is not related to y, right, I get a small amount of variance inflation, and then I get a huge amount of variance inflation. My standard error from the original goes up 3 times by including x3, which, as we note, is highly related to x1. So the more correlated your regressors are, the more variance inflation you're going to see. So there is these things called that look at this called variance inflation factors. And I just want to highlight this point. Notice variance inflation was much worse when we included a variable that was highly related to x1. And then, you know, we don't actually know sigma, so we can only estimate the increase in the standard error of the coefficients for including a regressor. So when we take ratios, the sigma drops out. So we can actually calculate the percent increase or decrease in variation explained by including an extra regressor. So when the regressors are orthogonal to the regression or regressor of interest, there is no variance inflation. So what they define something called the variance inflation factor, which is the increase in the variance for the ith regressor compared to the ideal setting where it's orthogonal to all the other regressors. And the square root of the variance inflation is the increase in the standard deviation instead of the increase in the variance. And then I just want to say, remember, variance inflation is only part of the picture. We may even want to include a variable even if it inflates the variance of our variable of interest, because it's important. It's an important thing to adjust for. So let's revisit our previous simulation. But notice, let me just say something. Remember, in our simulation, there was 3 things. There was y, x1, x2, and x3, and we simulated a new y x every time, but our x1, x2, and x3 were constant at their original value, and then we added, I guess we simulated errors each time. So what we're going to talk about actually doesn't depend on either y or the errors. It only depends on x1, x2, and x3. So you can calculate this for any given problem. So say we're interested in variable x1, and what's the consequence to the real standard error for including x2 versus including x3 in terms of the true standard errors expressed as a ratio of the standard errors. So this summary of this linear model fit, if you grab the unscaled covariance, the 2,2 entry is this variance for beta 1 in this case. And that's maybe a bit detailed, but it's true. So just trust me on that if you don't quite get that. But so what I'm doing in each of these cases is getting the standard error sigma beta 1 hat which involves sigma hat, divided by some function of the x's. Okay, and so we're going to take ratios. This sigma hat will drop out, so the fact that we estimated sigma hat won't matter. Okay, and from that we can see the variance inflation, and so here I divide the variance, the variance of the coefficient in front of x1. I divide the standard error for that coefficient, the variance for that coefficient, by what we get if we only include x1 to if we include x2, and what we get if we include x3. See, I divided it by a, where I defined a up here. Okay, so what this means is we get a 90% increase in variation from the model that only includes x1 by including x2, and we get a 9-fold increase in variation by including x3, and that's exactly what we saw in the simulation. But notice these are things we can do in our actual data. We don't need a simulation. Okay, and in fact I can show you via the simulated data, if I were to just take my simulated betas and calculate the variance, right, and get the variance for if I just have x1, if I have x2, and if I have x3 included, x2 and x3 included, and I take those the variances for if I include x2 and x3, and I divide it by the variance if I only have x1, I get the numbers that are very similar, and if I were to simulate enough, I would get exactly the same numbers as these. So let's just do this show how to do this in our data set. So I'm interested in, let's say, the agriculture coefficient from this Swiss data, and I want to know what's the variance inflation by including examination and education, and examination and education together. So I get sort of that 90% increase in variance when I include examination, and then 100% increase in variance when I include examination and education. Now again, this is variance inflation is just part of the picture. I think in this model we would want to include those because we would want to see, is the agriculture effect attributable to some of these other effects. So, and you can get the variance inflation factors, which is you get a variance inflation factor for every coefficient, and it's the comparison of how much variance is increased compared to if all the covariates were orthogonal. And you can see some of them, it's clear things like education and examination are very high, right? Because they're very correlated with each other, right? By the way, I like square rooting the variance inflation factors. The standard deviation inflation factors instead, I guess. But that's, so you can use these to see kind of for a given covariate how much variance it appears to be adding relative to a model where had all the covariates been orthogonal. Okay, so what happens to residual variance estimation when we forget or omit or include variables that we should have or shouldn't have? So again, we're going to assume the model is otherwise right. So linear IID errors, finite variance. Then we can describe the mathematical impact of omitting necessary variables or including unnecessary ones. So if we underfit the model, i.e. if we don't include necessary variables, we omit necessary variables, then the variance estimate is biased. If we overfit the model, then including all necessary covariates and unnecessary covariates, then the variance estimate is unbiased. So expected value, let me just So in that case, if we include all the necessary covariates and any unnecessary covariates, then expected value of sigma hat squared is sigma. However, the variance of sigma hat squared, including unnecessary covariates, is going to be greater than the variance of sigma hat squared, including only the correct covariates. So there is no free lunch. You can't just say throw in all the covariates and I'll get an unbiased estimate of sigma squared. There's a consequence. The variability in that estimate of the variance gets worse. Okay. So covariate selection. I'm not going to talk too much about covariate selection because we have an entire class on machine learning, and that's kind of the modern way to think about it. But automated covariate selection is a difficult topic, and it's and it depends on how rich of a covariate space you want to explore. Even with small numbers of regressors, the space of models explodes quickly as you add interactions in polynomial terms. And so in your prediction class, you'll cover many methods for traversing very large model spaces for the purposes of prediction. If you want to do regression, things like principal components or factor analysis models are often useful for taking complex covariate spaces and reducing the dimensionality. I would say if you're really interested in parsimonious small effects, then consider focusing on design, right? The best example is randomization. But you could also have things like randomization, stratification, and other things that can make your regression model not have to be very complicated because you've put a lot of thought into the design. So if models are interested in, if the models that you're interested in comparing are nested, in other words, one is a special case of the other with coefficients set equal to 0, and there aren't a lot of parameters in differentiating the two models. So if you want to compare a model with two terms in it to the model without those two terms, then you can just use nested likelihood ratio tests, and I'll show you how to do that in R. If you have zillions of variables that you're choosing whether or not to include, then probably you don't want to do this. But if you just have a couple, then this is a reasonable thing to do. My favorite approach is I tend to think in terms of scientific context, and so if I see an effect, a treatment effect or something like that, or an effect due to some important variable, then I like to use my modeling as a way to probe and test the robustness of that effect. Does my treatment effect, does it go away if I include age? Does it go away if I include BMI? And it's an approach of tinkering around with the models and seeing how robust the effect is to other variables included or excluded. And that's kind of a non-systematic process, but I feel like when you do that, you learn a lot about the data, and that's why I like it. And it's completely non-automated, but I do like to think about things that way. It would not work for things like prediction, but it does work extremely well for doing things like trying scientific discovery. So at any rate, if you want to do nested model search, right, if you want to do a nested model search, so take as an example, I'm interested in this agriculture coefficient, but I want to know whether or not I need to include the educational covariates as a group, and then whether I should need to include these other covariates, Catholic and infant mortality, as a group. If you just fit all three models, and the update function just says keep everything the same except in this case, the model, then the ANOVA function will create this series of likelihood ratio tests for you. So here, the output, it gives you the models that you're fitting. It gives you the degrees of freedom, which drop down. So we start out with 45 residual degrees of freedom. That's n minus p, and then we lose 2 more because we've added 2 more coefficients, and then we lose 2 more because we've added 2 more coefficients. So this degrees of freedom is the degrees of freedom for the comparison. So the comparison between these two models, you have 2 parameters difference. For the comparison between these two models, you have another 2 parameters difference. So this comparison compares it to the previous one. So it compares 2 to 1 and then 3 to 2, and that's what that p-value in each case is giving you. So in this case, it's saying, the p-values are saying, yes, that you should include these educational components, and then the p-value is saying, yes, if you include the educational components, then you should also include these Catholic and infant mortality variables. So that's how you can do nested model testing in R. The one thing is you had to have this ordering, right? You had to have agriculture, then this block of variables you were going to include in the second model, and this block of variables that you were going to include in the third model. So if your thinking and strategy fits into that framework, then that's a very good thing to do.